So hi everybody, and welcome to our webinar about API fuzzing of e-commerce platforms. So in this webinar, we'd like to talk about testing e-commerce platforms and web applications in general, and just show a demo also what we do in order to make this process easier and more efficient. And so before we start, so just like to introduce myself a little bit. I am Khaled, one of the co-founders and the CTO of Code Intelligence. So previously, I mainly did research in binary code analysis and vulnerability discovery. At Code Intelligence, I'm mainly responsible for our product and engineering and making a product that's really effective and easy to use, and so that our users would can benefit from this very effective technology. And just before we start, we will send the recordings to you. This was in the email. If you would like to get the recordings, just click on the confirm button in your email, and then a recording of this webinar would be sent to you. So the main topic is e-commerce and e-commerce applications, and their trust is a key thing. So when you buy stuff on the internet on an e-commerce platform, there you have sensitive information, you have your payment, you have credit card numbers, your method information about your payment method. So we have security, that's a very important aspect, and also availability, the meaning that your shop or your platform needs to be available all the time and does not go offline as a result of some bugs or denial of service attacks. And we had this with our users, seeing cases where you can basically take a shop offline, and this kind of attacks, these kind of vulnerabilities are basically can be completely seen by the users, would cause direct financial loss because the service is offline, and indirect loss because users would have less trust in the platform. So I think I don't have to convince you that testing or security testing is essential for these type of applications, but we'd like to talk about what is the most effective ways to test for security. And for that, so the main topic is fuzzing, as this is what we mainly do here at Code Intelligence. And so before we dig deep into some demos or what we do, just to give a brief introduction, what is fuzzing actually. So the core idea of fuzz testing is pretty simple. So you have a system under test you would like to test for bugs. You just have a fuzzer that throws some random inputs on this system and just check if the system crashes. And this approach was started like more than 30 years ago, where and it was used to test some Unix utilities, and it proved to be very effective. But you can directly see the limitations there. Just simply throwing random inputs in an application that maybe expects more structured inputs may lead to find some shallow bugs, but it would not help you finding the deeper bugs, let's say. And then came the idea of, okay, so let's take an example that we have an image parser that we'd like to test. So it takes images, it processes images. And the second advancement of fuzzing was, okay, let's an application that we have unit tests. And for these unit tests, maybe you have some example data. And so let's give this example data to the fuzzer. And the fuzzer would then try to do some mutations based on existing data. And for this, it can try to maybe find deeper bugs. So it can mutate some bits and bytes. It can change the color, etc. But some mutations might render the format of your inputs incorrect, meaning that you just generate some invalid inputs. And the real advancement in the area of fuzzing started 2013 with AFL, and there was the core idea the following. So the core idea is based on an instrumentation, meaning that we add specific markers to the code, into the code, and these markers then give the fuzzer feedback about which code areas have been covered, what kind of computations are happening in the software with a given input, and this enables the fuzzer to just check if the input I provided to the application was a good one or not. And so let's take this example, this image parser as an example. And so the fuzzer then would start maybe with an empty input, and the kind of feedback that the fuzzer would then get is something like this. You see, here is with this input, you manage to trigger these lines of code, and we see that all if statements are false because it was an invalid input, and this is the kind of input that the fuzzer would then get. Also, it would get information that the bytes the input that I provided was compared with these magic numbers. We see these FFD8 in hexadecimal. And so this the fuzzer knows because it instrumented the code, so it knows that these comparisons happen. So what the fuzzer would then do, so of course this is an invalid image, so what the fuzzer would then do is, let's try to use this constants as in my mutation, so in the next input. And then this would enable the fuzzer to trigger now the true branch of this if statement, and it would lead the software to think that it's dealing with a JPEG image. And this is this kind of loop, this kind of mutations happens several times, like thousands of times a second, and the fuzzer would then, at some point, it would be able to generate a valid image. And this was an experiment that actually done with the AFL fuzzer, and after a few hours, the fuzzer was able to generate valid images, even it didn't know that it's dealing with the image processing software. So then we get, and this, as mentioned, this kind of mutations, they happened tens or hundreds of times a second. And then the fuzzer would just keep using this feedback, keep the interesting input in the program that maximize the code coverage. And so at a high level, we can think of this method as, so we had the old school, the black box fuzzing, where you just provide an input and you'd have no idea what this input actually triggers in the application. But with the code instrumentation, and this is with white box fuzzing or the gray box fuzzing as we do it, you get exact information, where have you been in the code, and this way it enables the fuzzing or the mutation algorithm to find inputs that maximize the code coverage. And this just to show the effectiveness of fuzzing, as is done by the big guys. Google and Microsoft, they find 80% of the bugs using fuzzing only. So fuzzing there is the only testing method there. And if we have a look here at Google Chrome, where we see that fuzzing managed to find almost 22,000 bugs in a software code base that is written by really, really good engineers. So this shows how effective fuzzing is. But on the other hand, if we look in the industry, we see that fuzzing has not yet seen really wide adoption. And this mainly because it's still quite hard to integrate into development processes, into the development, the software development lifecycle. And this is what we are trying to improve. But then if we have a look at what kind of testing you currently do in let's take the e-commerce as an example. So you either do manual testing, where either just with some penetration testing, and this is really time consuming. You need real experts for that, and this is hard. It's hard to automate, like to integrate into the development lifecycle. And it's known that bugs are easier to fix and less expensive to fix the earlier they are found in the development process. Because ideally, you just commit the code, you see that something that you broke something, and you still have a fresh idea about what changes you did to your code, and it becomes really easy to fix. Otherwise, if you wait for weeks or months, then you may have forgotten why have you done something. And then we have the static analysis, so analyzing the code without actually executing it. And there, this can be very well integrated. You don't have to have a run environment of your code, but the main disadvantage there is that you have to deal with large number of false positives. So you have to filter out these false positives, or false, or you miss something, it's a false negative. And you have the dynamic testing. So you can do black box testing, you can do feedback, you can do fuzzing, and these it's very effective. You can find a lot of bugs with that, and with no false positives. So, and if we have a look at these testing methods, so the first two are really based on our talks also with the users, are really insufficient because you get large number of false positive. They're harder to automate. And with the dynamic testing, it's really effective, and this also goes to fuzzing, effective and scalable, but it's rather complex. And this is in this webinar, we would like to show what are we trying to do in order to make this integration easier, so that we can benefit from the effectiveness of fuzz testing as the big guys. So ideally, so here are we see, just to have an impression about these challenges, when you want to integrate fuzz testing into your continuous integration or into your development lifecycle. So the first challenge is that you would like to have an easy setup for continuous fuzzing in CI/CD. So ideally, each time you commit new code, new changes to your code, these changes would then be fuzzed, and then you get the results. And this is really important to guarantee the security of the software. And according to a study by Google, and OSS Fuzz is an open, it's a framework or a platform by Google to fuzz open source software. 40% of the bugs that have been found, or that are found there, they are regressions, meaning that these are bugs that have been added to to the application in the last 7 days. This 40% is like, it's a big number, and it shows like with continuous fuzzing that you can address these bugs quite easily and just fix them before they reach they end up in production. And if we think about e-commerce platforms or web applications in general, there we have highly structured input. So it's not like we're consuming just raw buffers that we can mutate. So if we have a REST API, each endpoint expects a request with a certain format, a suggestion format, and it needs to be these fields. And so this is something that you cannot directly do with the traditional fuzzing methods. And here we're talking about, so mostly we're talking about Java or JVM based applications. And these are, because traditionally fuzzing is used for memory unsafe languages like C and C++. And here we're interested in other types of errors, like as an example, the OWASP top 10, like the SQL injection, the cross-site scripting, and these kind of bugs. And the main thing that we would like to be able to do is to achieve this, is to instrument the code. And currently there are actually no good JVM-based or tooling for effectively instrumenting JVM-based languages. And would like to show a small demo or a workflow, how this looks like with CI Fuzz. And then just a small thing that our core, that we'd like to announce, our core Java fuzzer, including the instrumentation and testing, performing this fuzz testing on the API level, will be open sourced quite soon. So stay tuned for that. But for now, let's see the whole picture and how this integration of fuzzing would look like. So in this graph, in this diagram, we show the steps that you need to do, or that needs to be done ideally when fuzzing is integrated into your development lifecycle. So you start with this, your setup, you create your fuzz test, then each time you push your code or on a pull request, your code gets instrumented, gets fuzzed, you get to the report with the findings, and then you just then you have the finding, you can easily debug and fix them. And we'd like to show what we do in order to facilitate these steps. And just to give an impression how this would actually look like, let's start with the last step. So with the end goal, assuming that we set up everything and then fuzzing has found an error, what can we do to easily debug and fix the error? And the great thing about fuzzing is that with each input, with each bug report or vulnerability report, you get a concrete input that triggers this bug. And there you can easily start a fuzzing session or a debugging session with this input so that you can understand what's going on much more easily. And let's see how this would look like, or how this looks like in CI Fuzz. So here we see WebGoat. So WebGoat is a Spring Boot application, mainly written in Java by OWASP. And the goal of this application is there are certain vulnerabilities. So it's being deliberately insecure that can be used to show different types of vulnerabilities. And we set up fuzzing for this project so that fuzzing is started on each pull request. And let's have a look then at the pull request here. So we see that this pull request has failed. And if we have a look at why it's failed, it failed because Yeah, because we found in this run an SQL injection problem, and there you get with CI Fuzz, basically you get a bug report, and you get in your pull request also information about code coverage that you achieved in this fuzzing run. And now, if I want to have a look at a more detailed information about the bug report, I can click on View Finding, and this takes me to our platform, so the CI Fuzz platform, where I can have like more details about the finding. And let's have a look at it now. So, and here's the example. So we see that in which source file this this bug has been found, and we see the concrete request that the fuzzer has sent to the application, and we see that okay, it was a post request. It uses a username Larry and add some password, and this is we'll show the details how the fuzzer achieved that in later. But now what I can do is I can see here debug in VS Code. And what this would do is it would just create a debugging session in my IDE locally with this crashing input. So as a developer, it becomes really easy for me to understand what's going on. And let's try this out right now. And yeah, of course, this now I have, this is opened in VS Code, and this is really a very large project. So it takes a few seconds for it to be started in the debugger. But so this is also an opportunity to mention that we also have this, what you see, this experience in VS Code, where you can set up fuzzing in the IDE. So now, we saw that here as interesting, you see that these breakpoints, so this were automatically set. And we do this because from the fuzzer, we get a complete stack trace of what went wrong. And we can basically then, so that it's easier to step through the code to observe the errors. And so it will be finished soon. Yeah, it's a large application. It needs some time to start. But then this example would also enable us to show the effectiveness of gray box fuzzing. So now I can then step here and I go directly into the location where an XUL statement is evaluated. And here we see, so we saw in that example that we create a username Larry and this password. And this is why fuzzing is great, because you can, with this concrete input, you have a concrete example that triggers this bug, and then you can have a look about, as a developer, it becomes easier for you to understand what's actually going on here. And interestingly, we see in this code that in this code block here, that username is actually, there's a comparison between the provided username with Larry. And of course, the fuzzer didn't know this beforehand. So how the fuzzer was able to actually crack the username. And this is because of the instrumentation, because we basically, as mentioned, instrument everything and report this information to the fuzzer. So the fuzzer would then just see that the username is compared with Larry, and it would use it in the next iteration, basically. So with this we show how we can easily go with fuzzing or CI Fuzz from your pull request to view the finding to start a debugging session where that makes it easier for you as a developer to understand the bug. And so this takes us to the reporting part. And of course, in the web app, you can view you can view the findings. You can have reporting of all findings. You see exactly what went wrong. You see you can filter for several types of vulnerabilities, and yeah, you have an overview about yeah, how many errors you have in each with each run, and of course you can easily export the report and stuff like that. So this shows how can and here we see yeah, different type of uncaught exceptions and yeah, stuff that errors that that have been found in this run actually. So, and now that we saw that reporting, how reporting looks like, just talk to in order to produce this report, we fuzz, and of course we perform this in don't want. I don't think I want to go into too much technical details unless you have questions, of course. But we call ensemble fuzzing, meaning that we combine different fuzzing strategies, different mutation strategies, so that they can work collaboratively with each other to achieve the best results. And in the platform, we take care of instrumentation, of orchestration and monitoring automatically. And then this takes us to in order to be able to do this effective fuzzing, we need to be able to instrument the code. And with this instrumentation, we base our instrumentation on the Java bytecode, meaning that we don't require the source code in any way, but we instrument the Java bytecode. This makes it more flexible to use it with other JVM-based languages like Kotlin, for example. And this instrumentation part is included into or will be included into the Java fuzzer that we will be releasing soon. And so, in order then just to create the fuzz test or to perform fuzzing, we need to create the tests. And this is one issue that we talked about, like with web applications, you deal with highly structured inputs. So you have endpoints that have special requirements on what kind of requests they accept, and it simply doesn't make sense to just send completely random data to an endpoint that accepts JSON requests of a certain format. And for several frameworks, we automated this creation of fuzz tests completely, as in this example of Spring Boot, and we'll just show how we do that. But for other frameworks, we can just provide an open API or Swagger definition, and this would be understood by our fuzzer, and it can then, based on that, performs fuzzing or smart mutations or structure-aware fuzzing automatically, because it understands the structure and it mutates it in a way that all the time produces valid inputs. So now, let's go back to the IDE here, and here we see our plugin. And now, if I would like to create a new fuzz test, so I just click here. I want to add a new fuzz test. And here we see the types of fuzz tests that we provide. And so this would like here in this case to add web app fuzz test. And yeah, we see here the list of controllers, the list of endpoints that we automatically resolve in an initialization step. And now all I have to do is just select which endpoint I would like to fuzz. And of course I can search here. and select the endpoint I would like to fuzz and just click on save. And this automatically then, I have to fill the name. And this would automatically generate a fuzz test here. And we see here in this example that of course, we know the format. We know that this expects a username and a password, and we just know what are the parts of the request that we can or that we should mutate. And of course, if your request of your application expects basically some login or some initial request that you have to send it to it before being able to interact with the application, then this can be also configured. And this way you can just, with zero effort, just select the endpoints that you would like to fuzz, and the fuzz test, the corresponding fuzz test, will be generated automatically. And now all I have to do is just basically start the test collection, or which is the runtime configuration, and then we instrument the code automatically and then run this test. And yeah, so in order to be able to do that, basically, we do a simple setup step where we just build the code once, analyze if this contains any applications that we know of. And then for these applications, in this case, Spring Boot, we just analyze the endpoints and enable you just to create these tests automatically. And with that, here we've seen basically the complete workflow, what you need to set up the test, to set up the project, set up fuzzing, create the test, and how instrumenting and fuzzing and reporting happens automatically and how they look like. And when fuzzing finds an error, how easy it would try to make it in order to for developers to understand and fix the bug. And so this is what we think is a very good way to integrate fuzzing into development processes, and this becomes part of the continuous integration where each time, or on pull request, or depends on how you configure it in your CI/CD, to trigger fuzzing so that you can benefit from continuously fuzzing and testing your application so that bugs are found as soon as possible. Yeah, so this brings me to the conclusion. So we've seen, as done by the big players, that fuzzing is currently actually the most effective method of finding bugs, and that we showed also how we try to easily integrate this fuzzing, this effective technology, into the development lifecycle, so that not only Google and Microsoft can do it, but all with the vision that enabling all developers to do that. And of course, if you need more information or questions about the platform, you just can contact me or write to me, or write to me on Twitter or my email. And as a final remark, also stay tuned for the open sourcing of our Java fuzzer, which is orders of magnitude more efficient, more effective than what's currently available as open source tools. And yeah, so just to finish, so this how when you have a secure software, when it's being fuzzed, then you hopefully will have easier time not worrying about everything that can go wrong, because fuzzing will find many of them for you, and so that we try to make you all also sleep well, not only the big guys at Google and Microsoft.